Thank you for watching our video. I'm Naoki Kai from Nagoya University, Japan. In this video, I will talk about navigation style classification using persistent homology. Before talking about the main topic of this work, I would like to share with you about our fundamental motivation for this work. Recently, in the mobile robot field, many researchers study about socially aware navigation. In such work, researchers are focusing on human-robot coexisting environment, and they will try to realize human-friendly navigation. However, it is difficult to define what is socially aware and human-friendly behaviors for mobile robots. Consequently, it is also difficult to evaluate whether a developed navigation method is socially aware or not. To tackle this problem, we conducted a simulation experiment that was designed in terms of the traffic psychology. In the experiment, 29 subjects were employed, and they moved an ego agent to the destination with a joystick. We instructed the subjects about please cooperatively agently and non-agently navigate the agent. Here, we assume that the navigation with cooperative instruction could be the socially aware navigation, because this style well fits to Japanese common sense. To tackle, the left-hand video is examples of the experiment. The subject moves the blue agent to the destination, indicated by the square. Other agents, depicted by the gray, are randomly moving. In the experiment, we found that the significant difference can be found in the acceleration. The large acceleration was seen in the cooperative case. We consider that in the cooperative case, the subject suddenly changed the movement of the ego agent because they concerned other agents. However, even we can see the significant difference in the acceleration, it is super difficult to distinguish navigation style from the movie. This fact motivated as can we distinguish the navigation styles using surrounding information of the agent? If we can distinguish, we could find patterns to distinguish the navigation styles, and we could discuss what kind of behavior can be regarded as socially aware based on some numerical values. Now, I would like you to share with what this work does. We try to classify the navigation styles using the persistent homology. As the next, I will explain about the persistent homology. As I showed you, we conducted the simulation experiment and found that the significant difference can be found in the acceleration. However, it is difficult to find patterns from surroundings of the ego agent. We consider that the ability of the persistent homology might enable to detect better patterns. However, unfortunately, we could not achieve better classification using the persistent homology. However, we believe this work could be a better first step for this field. Okay. Let me first explain about the persistent homology. To share with you about the persistent homology, first, I would like you to introduce topological data analysis that is default to TDA. In TDA, dataset is regarded as a point cloud, and its geometric property is analyzed in terms of the topology. There is a very famous example in the topology, that is, donuts and mag are the same in terms of the topology. Both donuts and mag have one connected component and one hole, respectively. In the topology, we do not focus on exact shape of target geometry. Instead, we focus on the numbers of holes. To simply say, we compare the homology of geometries. Consequently, we can say that donuts and mag are the same. However, point cloud does not have boundaries, and it's difficult to define exact holes in point cloud. For example, in the right-hand figure, maybe we can say this geometry has one connected component and four holes. However, we do not have exact boundaries as shown in the figure. Consequently, we do not have exact evidence that this geometry has one connected component and four holes. Basically, point cloud does not have connectivity information, and we cannot say exact numbers of the holes. A sophisticated method is required to calculate topological features for point cloud. The persistent homology enables to calculate the topological features from point clouds. The bottom figures show concept of the persistent homology. First, we have point cloud as shown in the left figures. Circles, left figure, sorry. First, we have point cloud as shown in the left figure. Circles are set to all the points and their radi increase. In the middle left figure, we can see a hole since the circles are connected. This moment is default to birth. The radi of the circles increase again. And finally, we cannot see the holes as shown in the middle right figure. This moment is default to death because the hole disappeared. After all the circles are connected, we can obtain many birthday pairs from point cloud. These birthday pairs can be plotted on a 2D diagram as shown in the right figure. As I explained before, the birthday pairs can be plotted on a 2D graph. This graph is default to persistence diagram. A persistence diagram summarizes topological features of the target point cloud. The persistent homology is widely used in descent. This is an interesting example of the application of the persistent homology. Molecular distribution of liquid and gas seem to be randomly distributed, as shown in this figure. And it is difficult to distinguish them from the distribution directly. However, specific patterns can be found on their persistence diagrams. These results show that the persistent homology enables to extract characteristic topological features from patterns, even though they seem to be random. We focus on this ability of the persistent homology. We create 3D point cloud from relative flows of the other agents. The ego agent moves by the joystick command, and its relative flows to other agents changes. We plot the relative points according to the time axis, and we can have 3D point clouds as shown in the bottom figures. The left and right figures are obtained when the navigation instructions are set to cooperative and agent respectively. However, it is difficult to find specific patterns from the point cloud. Hence, we apply the persistent homology to the points. We generated persistence diagrams from the point cloud. The bottom left and right figures are the persistence diagrams generated from the cooperative and agent results. There might be some differences on the diagrams. So there are efficient methods that enable to create fixed size vector from the persistence diagrams. If we can create fixed size vectors, we can easily use machine learning algorithms for the navigation style classification. Professor Obayashi presented persistence image that makes image data from the persistence diagram. We use this method and apply machine learning algorithms for the classification. This slide shows the navigation style classification results. We applied 4 methods for the classification. Logistic regression and support vector machine takes the persistence image and classifies the navigation styles. In this experiment, we use the same numbers of data for each navigation style. Hence, the chance rate for the classification is 33%. In other words, logistic regression and support vector machine could not distinguish the navigation styles. We also applied k-nearest neighbor with the vector created from egg motion information. For example, this vector has average of velocity and acceleration of the egg agent. As I showed you in the first, there are significant differences between the acceleration, hence the egg motion-based classification works. We also applied a hybrid method that uses the logistic regression, egg motion vector, and the persistence image. This method slightly outperforms the egg-motion-based k-nearest neighbor. However, we could not confirm drastic improvement even when the persistence image is used. These results show that it's not easy to classify the navigation styles even if we simply apply the persistent homology to the relative raw data. Let me conclude this work. In this work, we focus on can we classify the navigation styles from surrounding data. The motivation of this work is that we would like to obtain patterns of surrounding situation to classify the navigation styles, and we would like to know criterion to evaluate the navigation styles. To achieve this motivation, we created 3D point cloud data using relative points from ego agent to other agents. The relative points are plotted according to the time axis, and we can have 3D point clouds. We apply the persistent homology to the relative rows and created vectors that represent topological features of the relative rows. We then apply machine learning algorithms to classify the navigation styles. As a result, we could not distinguish the navigation styles with a persistent homology. The egg motion information was dominant for the style classification. For the future work, we consider that a better vectorization method for surroundings is necessary to classify the navigation styles. We would like to consider how we can achieve this. Also, applying the inverse analysis presented by Professor Obayashi is interesting because it enables us to know which point patterns are effective for the classification. Thank you for watching our video.